Welcome back. With all the work we've done on cyclic subgroups, we're now in the position to state the so-called fundamental theorem of cyclic subgroups. This is the one that kind of summarizes what we know about them and especially tells us about how many subgroups a cyclic group has and what they are. Right, so here it is, the fundamental theorem of cyclic subgroups. Now this says a lot. So we better go through it fairly carefully, so that we make sure we understand what it's actually claiming. So first off, it says that every subgroup of a cyclic subgroup is cyclic. So you cannot have a non-cyclic subgroup of a cyclic group. And that's the first part. The second part is that if you have a cyclic group of order n, then the order of any subgroup is a divisor of n. That's pretty cool. And for each divisor, there is only one subgroup. So essentially it's saying that we can find all of the subgroups of a cyclic group just by finding all of the divisors of the order of the group. Right, so we've got a bit of work to do to prove this thing, but once we've proven it, then we can suddenly know a lot about how subgroups of cyclic groups work. In fact, we know everything. So here we go, proof. So the first thing we have to prove is that every subgroup is cyclic. So we'll start with that one. Every subgroup is cyclic. Right, so where will we start? So we're going to just set up, again, like we normally do, we'll set up our actual problem. So we've got a group G, which is generated by A. So here's our cyclic group we're going to work on. And let H be a subgroup of G. Now the most basic case is if H is just the trivial subgroup, then it is cyclic. And we're finished. So we're going to assume from now on, otherwise, we can assume there is some other thing. Let A to the T be a member of H for some positive integer T. Okay, we know G is a cyclic group which is composed of the powers of A from the identity up to n minus 1. Therefore, if our subset of this is not just the identity, then it's going to have some positive power of H. Okay. Right, now H is a subgroup, so that means A to the minus T is also going to be in H. So by closure, A to the minus T is a member of H also. Okay, so we've established that we have some A to the T in our H where T is a positive integer. So because we have a positive integer one, we can now choose the least of these. So let M be the least positive integer such that A to the M is a member of H. Now it might be the A to the T that we chose to start with, it might be a smaller one, but M is the least of these. Now what we're going to try and do is we're going to show that actually this subgroup H has got to be the subgroup generated by A to the M. We will show that H has to be this thing here. Okay, so by closure, because A to the M is in H, all powers of A to the M must also be in H, so let's just put that on a new line. By closure, the cyclic subgroup generated by A to the M is contained within H. It has to be, otherwise A to the M couldn't be in H. Now we need to show that there cannot be any other things in H that are not in that cyclic subgroup generated by A to the M. Okay, so let B be some other member of H, I want to show that B must be included in the cyclic subgroup generated by A to the M. Now, I'm going to use the division algorithm again. Because we know that we have this idea that M is the smallest integer such that something happens. And remember, the division algorithm lets me turn a number into something smaller than that thing. So by the division algorithm, K is equal to QM plus R for some Q and R in Z, with, in particular, 0 is less than or equal to R is less than M. And again, like we've used it in the past, the idea here is going to be to show that R has to be equal to 0. Thus, B equals A to the QM plus R equals A to the QM, A to the R, which implies that A to the R equals A to the minus QM times B. Okay, now how does that work? Well, B is in H, A to the minus QM is in H, has to be because our subset here is contained within it, and this means that A to the R must therefore be in H. But R is less than M, and we said that M was the smallest integer such that A to the M is in H. So it's this usual argument is worked out again. So by closure and inverses, A to the R must be in H, which implies that R equals 0, as R is less than M, and B is therefore equal to A to the M to the power of Q, which is, in fact, a member of the cyclic subgroup generated by A to the M. Okay, so what's the logic we've done here? Well, we first off chose the smallest positive integer power of A to be in our arbitrary subgroup of G. We showed that the cyclic subgroup generated by that was contained within it, and then we tried to find another element that might not be inside this cyclic subgroup, and we showed that it had also inevitably to be inside the cyclic subgroup also. Therefore, H is equal to the cyclic subgroup generated by this A to the M that we found. Okay, so we've proven the first part, which is that every subgroup of a cyclic group is in fact cyclic. Okay, let's prove the next bit. If the order of our cyclic group is n, then the order of a subgroup is a divisor of n. How's that one going to work? Well, we'll choose ourselves a subgroup of our cyclic group. We know that all subgroups are cyclic also, which means that we can write H as the cyclic subgroup generated by A to the M for some positive integer M. Then the order of the cyclic subgroup generated by A to the M by our theorem is equal to the order of A to the M, theorem from the previous video, which equals the GCD of N and M. Okay, by theorem 4.2. Okay, so the order of that subgroup, we've actually established how that works, is the GCD of N with M. Okay, finally, the last thing we have to prove is that there is exactly one subgroup of order k. So, exactly one of order k, which is a to the n over k. Okay, so we'll do the usual thing, and we'll assume there are two and show they must be equal. So we'll let there be two cyclic subgroups of order k. Where these things are both subgroups of order of a to the n. Okay, and then we can just use our corollaries to theorem 4.2 to say that then GCD of Ni is equal to GCD of Nj, which in turn implies that the two subgroups are equal. And finally, the order of a to the n over k is equal to the order of the cyclic subgroup generated by a to the n over k, which is n divided by GCD of n and n over k, get in there, equals n divided by the greatest common divisor of n with n over k is quite clearly going to be n over k, which equals k. Okay, so we showed that if there were two subgroups of order k, they have to be the same thing, and then we calculated the order of the cyclic subgroup generated by a to the n over k, and showed that that is the one that has order of k. Alright, so that's the fundamental theorem of cyclic subgroups. Next we're going to take a look at how that applies to Zn, because as I've mentioned previously, when we're talking about cyclic groups, it kind of makes sense only to think about Zn, because that's the one that's most relevant, and in a sense, all other cyclic subgroups work the same way as it. So we'll focus our attention on that in a second. So here's the same theorem, basically expressed for Zn, and this says that for each positive divisor k of n, the set generated by n over k is the unique subgroup of Zn of order k, and that these are the only subgroups of Zn. So we can look at an example of that. Let's find all of the subgroups of Z30. Okay, so divisors are 1, 2, 3, 5, 6, 10, 15, and 30. So these make subgroups. The subgroup of order 1, let's put them underneath, is going to be 30 or 0. Don't forget we're mod 30, so we can do that. Subgroup of order 2 is 15. The only subgroup of order 3 is 10. The only subgroup of order 5 is that generated by 6. Only subgroup of order 6 is that generated by 5, etc., etc., and 1. So these are the only subgroups of Z30, and those are their orders. Okay, another example. Find all generators of a subgroup, or of the subgroup, of order 9 in Z36. Okay, so we know that Z36 has a subgroup of order 9, and it's going to be generated by 36 divided by 9 is 4. Okay, so we know that 36 over 9 equals 4 is 1 generator. Now we're going to apply our theorem 4.2, corollary 3. Let's try that again. 4.2, which says that the order of 4 is 9, and that the cyclic subgroup generated by 4 is the same as that generated by 4 to the j, if and only if the GCD of n, which now is not 36, it's 9, because we're looking inside the subgroup of order 9. So n is 9, and j equals 1. So, numbers relatively prime to 9 are 1, 2, not 3, 4, 5, 7, and 8. So the cyclic subgroup generated by 4, which is the only subgroup of order 9 in Z36, is also generated by 8 and 16 and 20, which is 4 times 5. So it shouldn't be 4 to the j, so it should be 4j because we're in additive notation. Then we should have 4 7s are 28 and 32. Okay, so there's one other thing I want to talk about before we leave this video, and that is the so-called Hasse or lattice diagram. German word, so Hasse diagram. Essentially, it's a way of depicting the subgroup structure of a group. Depicts subgroup structure of a group. And the way we draw it is we say H is connected to K, where K is higher, drawn higher up on the page. Only if K is a proper subgroup of H, and if K is not a proper subgroup of a proper subgroup of H. Okay, so that sounds like a weird thing to say, so we'll just draw a picture of it with Z30 and see how it works, because it's actually not as bad as all that. So for Z30, our biggest subgroup is that generated by 1. Okay, and that contains all of the other subgroups, but I'm not going to draw a line to 1 from all of them because it's actually a little bit simpler than that. So I'm going to draw 2, 3, and 5 next. Okay, so these are all subgroups of the cyclic subgroup generated by 1, so I'm going to draw lines to those. Now, why did I not draw 6 directly connected to 1? That is because the cyclic subgroup generated by 6 is contained within the cyclic subgroup generated by 2 and by 3, and these are both proper subgroups. Likewise, 15 is in a similar boat. Okay, it is a proper subgroup of 1, but it's also a proper subgroup of 3 and 5, so we connect it up to 3 and 5. Then we have 10, behaving the same kind of way. It's connected to 2 and 5, so I'm just going to draw it a bit like that. Okay, because the cyclic subgroup generated by 2 and by 5 both contain 10. And then finally we have 30, which is 0, which is down here. Okay, so if I'd drawn that a bit nicer, it looks a little bit like a cube kind of thing. A little slightly out of proportion, but it looks like the map for a 3D cube. So you can see that we enumerate all of the subgroups, we figure out which ones are subgroups of which others. Here we can see it just that the ones higher up have to be divisors of the ones lower down. And then we draw lines connecting proper subgroups so long as there's no, we draw lines to proper subgroups and with the kind of precedence relationship that I've drawn here. So that's how we draw a Hasse diagram, and it's a nice visual way of seeing how all of the subgroups of a finite group fit together. So that's enough for this video. We'll catch you for the next one. We've got one little extra comment to make about these cyclic groups before we move on to our next topic. So there'll just be a little short addendum video to this one. And we'll catch you next time.